Hello. So now we'll study the Bernoulli's theorem. So this continuity theorem, which was based upon the conservation of mass. So similarly, this Bernoulli's theorem is based upon the conservation of energy. As the continuity theorem used to say, within the test volume, the mass will be constant if there is no inlet and outlet, external one. Similarly, Bernoulli also says within this test volume, the energy, total mechanical energy will be conserved if there is no friction acting within this test volume and if there is no external agent operating within this test volume. So if you remember this we learn in work energy theorem. So in case of work energy theorem, mechanical energy used to be conserved if there was no external agent and there was no friction there. So it is the same. It's just the extension of work energy theorem onto the fluid. So this is our test volume and we want to calculate what is mechanical energy within this test volume. And if we put a condition that there is no external agent and there is no friction there, we can conserve that mechanical energy. So first of all, let's write the conditions for Bernoulli's theorem. So if we talk about the conditions, the first and foremost condition is, as you know, streamline flow. The flow has to be streamlined, otherwise we cannot proceed any further. So if flow is streamlined, that's the first condition. Second condition is regarding the external agent. External agent. What is the external? Actually, there is no person who will be going inside. External agent in case of fluid means the pump kind of instrument. There should not be any external instrument which is operating within this test volume. There can be external instruments operating here and there, but the pumps kind of instrument should not be there within our test volume. So that is the external agent we are talking about. Third, friction should not be there, and in this chapter we don't call it friction, we call it viscous. Viscous force should not be there. These two things should not be there. And the streamline flow has to be there. So there should not be any friction force or viscous force. The static version of that can be there, and it is there actually. But the kinetic version of the viscous force should not be there. Okay? So if these conditions get fulfilled, in that case we apply the Bernoulli's theorem. So let's first derive that theorem. So this is our test volume and we want to conserve the mechanical energy within this test volume. So first of all, we have to calculate that mechanical energy. It's not that easy in case of solid we used to calculate. We just used to multiply mass with V square and we used to get the half mv square kinetic energy. It's not that easy. So we have to first calculate those energies. So mechanical energy consists of two types of energy, kinetic one and the potential one. And in case of fluid, there is a kinetic energy because flow is happening, and in case of fluid, the potential energy there are two types of potential energy. One potential energy will be there because of this gravitational force which is acting onto the fluid. Each and every particle is experiencing the gravitational pull. At the same time, each and every particle is experiencing the pressure also, which is generated by the other fluid. So pressure is nothing but the force. It's the application of force, but force divided by area, per unit area. That's pressure. So the force, pressure force, the force which is causing the pressure is also conservative. So in case of Bernoulli's theorem, we will study two types of potential energy. One corresponding to the gravitational force and the second corresponding to the pressure force. So let's first define the kinetic energy. So we will calculate kinetic energy first. The formula is same. There is no problem in the formula. So this is our test volume. This is a test volume which is having mass m and the volume is dv. The velocity is v, small v. So this test volume which is having volume v, mass dm, pressure p and the density rho here. So I'll calculate the kinetic energy for that test volume. So I'll call that dk. So kinetic energy for the test volume can be written as half dm v square, and this dm we can write it as rho dv v square. So this is the kinetic energy for our test volume. Half rho dv multiplied with v square, kinetic energy. Let's now calculate the gravitational potential energy. So gravitational potential energy, I am calling it PE. So we will calculate the gravitational potential energy for our test volume. For our test volume, so which is having dm mass. So you see, this test volume, this is the level. This is the level for Ug 0. At this level, I have assumed the gravitational potential energy is 0. We can take it at any level. We have taken it here. And from this level, the first cross-section area is at h1 height and the second cross-section area is at the h2 height. And the test volume is at a height of h. So we already know the formula. The gravitational potential energy, dUg, will be equals to, it is mgh. Formula is mgh, but here the mass is dm. So it will be dm g multiplied with h. So this is the gravitational potential energy for our test volume. So let's simplify it in terms of dV. So it will be rho g h times of dV. This is dUg. So this becomes the gravitational potential energy. So this is our second equation. Now let's go for the third equation, which is the pressure energy. We want to calculate the pressure energy. I should call it pressure potential energy. Let's call it pressure energy. So if I want to calculate the pressure potential energy, we have to calculate the force which is providing the pressure. So let's assume this is the derivation we are doing for the pressure potential energy. So let's say this is our test cross-section area. This is a test small cross-section area. I'm calling it capital A. So pressure here is P. And this pressure will cause some force which will be perpendicular to cross-section area. This is Fp I am calling. So if you know the value of Fp, we know that is P multiplied with A. And this Fp will be perpendicular to A. This Fp will be perpendicular to A. It is perpendicular to A, but it is parallel to A. A itself is a perpendicular to the cross-section area. So due to the application of this force, this cross-section area will move, and along with that cross-section area, each and every particle which is in this cross-section area will also move. So let's say due to this force, pressure force, this cross-section area has moved by a distance dx. This moved by this. So the work done, let's directly calculate. So potential energy due to pressure force can be defined as minus of pressure force dot displacement. That's a general formula for potential energy. Let's put the values. So it will become PA, and you see the pressure force and the displacement will be in the same direction because the displacement will be happening in the direction of force. So this dot product, when you will take the dot product, the displacement and the force is in the same direction, so it will be cos 0. So PA dx. Or we can say PA dx. Now you see here, this A into dx is nothing but the volume created. So this can be done as P dV. So dup becomes P dV. This is equation 3. Okay. So we have calculated the kinetic energy. This one is the kinetic energy. We have calculated the gravitational potential energy, and we also have calculated the pressure potential energy. Let's write the mechanical energy now. So for that test volume, we will write the mechanical energy dE, and that will be equals to dk plus dUg plus dup. If you put the values, it will become half rho v square dV plus rho g h dV plus p dV. That becomes dE. So for the test volume, mechanical energy becomes half rho v square dV plus rho g h dV and plus p dV. It is p dV. Now dV here is same for each because the dV is the test volume. So what can I do? I can divide this whole equation by dV. So if I divide this whole equation by dV, I will get the mechanical energy per unit volume. So that will be equals to half rho v square plus rho g h plus p. So during derivation, we got the mechanical energy per unit volume within this test volume. So now I have a formula for the mechanical energy per unit volume here, as well as here, as well as here, everywhere. And the thing is, we were saying within our test volume, mechanical energy will be conserved or constant if these three conditions are there. Within our test volume, mechanical energy was constant. So within the per unit volume also, because per unit volume is also a constant volume. So within the per unit volume also, the mechanical energy will be conserved, and the mechanical energy per unit volume is this. So this whole value will be constant. So now I can write half rho V square plus rho G H plus P is a constant. This is our Bernoulli's theorem. So half rho V square plus rho GH plus P is a constant. The thing is, this whole thing is a constant, not individual things. Out of these things, things will change. Basically, if you move from 1 to 2 point, the velocity will change. If the velocity will change, all the other things cannot remain constant. So since height is changing, velocity will change, or the velocity is changing, pressure will change. So this is the equation involving 4 variables: V, H, P and rho. Generally, as we know, the rho is constant. So this equation is the equation between 3 variables: velocity, height and pressure. So as one of those or the other 2 will change, the other thing will change. So as they will keep changing, but this relationship will also hold. So this is a Bernoulli's theorem. Let's see from the application point of view. So if examiner will be giving us the question, he'll be providing us some of these values at one point and some of these values at the other point. And there will be some unknown values. He will tell us to calculate those values. So as an example, we have taken the area, pressure and the velocity at this cross-section area, and we have taken the area, pressure and velocity at this cross-section area. And the thing is, if I take the unit volume here or unit volume here, the mechanical energy is going to be same. So unit volume here will have the mechanical energy per unit volume from this equation. So I calculate the mechanical energy per unit volume at the inlet, that will be equals to half rho V1 square plus rho G H1 plus P1. This is the mechanical energy per unit volume at the inlet. So this value will be equals to half rho V2 square plus rho G H2 plus P2. So this will be an equation. This will be the equation involving the variables at inlet and at outlet. So this will always give us the equation. You see. And one more thing, many a time examiner gives you the horizontal pipe. So when he is giving you the horizontal pipe, in that case H1 and H2 will be same. So for horizontal pipe kind of thing, H1 will be equals to H2, and you see these two values will cancel out. So this Bernoulli's theorem will convert into half rho V1 square plus P1 is equals to half rho V2 square plus P2. You see. Now one more time I want to repeat. This Bernoulli theorem, when we study this Bernoulli theorem, this is the relationship, this is the theorem which is related to the energy. So it says the mechanical energy within a test volume will be constant. It is nothing but the extension of work power energy. Only difference is, in case of work power energy, we used to calculate the energy in some different manner, and here it is involving the fluid. So we have to calculate these energies in different manner. So that's what we did. So what we did, we started with a test volume. This test volume we have taken, and at this test volume we have defined some variables. That's pressure, dm mass, velocity, this dv volume we have defined here, and density. So corresponding to these variables, we keep calculating the mechanical energy. And the mechanical energy has 3 components. One is the kinetic energy. We calculate the kinetic energy for the test volume. Then we extended this for gravitational potential energy. We calculated the gravitational potential energy for the test volume. And then we defined one more force, that was a pressure force. Actually, we have already defined that force. But then we said this force is a conservative force. So every conservative force has the potential energy. So we calculate the potential energy corresponding to the pressure force, and the formula comes out to be PdV. And all these energies we calculated with respect to the constant volume or unit volume. So dk by dv, we converted those. And when we did that, the mechanical energy per unit volume gets converted into this formula, half rho v square plus rho gh plus p. So this equation involves 4 variable or 3 variable if the density is constant. This is the equation we get. And this equation we can utilize in different manner. If there is a pipe which is varying in height, in that case, it's at the inlet, the examiner will give you some of the variables at the inlet, he will give you some of the variables at outlet, and you can always construct this kind of equation. It will always be an equation. If examiner is giving you the horizontal pipe, you again construct an equation. Some of the variables will be given and some you will have to find out. So it will always give you an equation. This is your Bernoulli's theorem, but you do remember for the Bernoulli theorem there are 3 conditions. This one, and this one. And if you remember, in case of continuity theorem, only this was the condition. These 2 conditions were not there for continuity theorem. These 2 conditions are added for Bernoulli's theorem. So the thing is, when the Bernoulli's theorem is applicable, all 3 conditions has to follow. So when all 3 conditions are following, this condition automatically will follow. So when the Bernoulli's theorem is applicable, continuity theorem will always be applicable. But when only continuity theorem is applicable, we cannot extend that for these 2. Because continuity theorem will be valid whenever there is a streamline flow. So if I want to define the concept, continuity theorem is a set, and out of that, Bernoulli is a subset. Bernoulli is only applicable when this is there, along with these 2 more conditions gets followed. Okay, so that we have to memorize, that we have to always remember. Okay, thank you.